So let's begin chapter 10. Chapter 10 is about hypothesis testing. And that's pretty much what we're going to be doing from here on to the end of the course. So it's going to be really important that we understand and take slowly the foundations of what we're doing here. Chapter 11, 12, and 13 are all full of hypothesis tests. And just a reminder, you're going to want the inferential statistics cheat sheet on you pretty much at all times from here on to the end of the course. For quizzes, for homework, for your exams, you want that inferential statistics cheat sheet with you. All right, now before we get into the process of the hypothesis testing, we have to learn how to set up several things. So the first thing we're going to do is talk about the base theory of what's going on. So let's suppose you're in a classroom full of students and everybody rolls a die and counts how many 5s there are in 12 rolls. Okay, so I'm going to simulate this right now with my lovely rand between function. So random rand between. I want to choose between 1 and 6 because I'm going to assume this is a 6-sided die. There are lots of ways to do this, but this is just how I'm going to do it. And there we go. And you can count how many 5s there are in any particular sample. So for me, watch this. Boom, it changes. Right? So the thing about the rand function, rand between and rand, any random function in Excel, is that everything is it's called a volatile function, meaning it will change every time. So if I type hi and press enter, boom, it changed. And if I delete it and press enter, oops, it changed. And it just keeps changing and changing. So don't freak out. But, you just need to look at it and go, oh, okay, well, I got 2, or I got 0, or I got whatever. So my particular one, I got 2. You can do whatever you like. Okay. Now, what conclusions might you jump to if these are your results in your class? So let me back up for just a sec so you can see. There we go. So we had 2 people that got 0 5s, 4 people got 1 5, 10 people got 2 5s, 3 people got 7 5s, 4 people got 4 5s, 1 person got 5 5s, 1 person got 6 5s, no 7s, no 8s, no 9s, no 10s, no 11s. And student Steve got got 12 out of 12 5s. He rolled it 12 times and got 12 5s. So what conclusion might you jump to about Steve? Well, there could be several things happening. So Steve had 12 out of 12 5s. So every roll he got a 5. Now, what are some possible options? So it could just be random chance, right? It could be he's lying, right? Maybe he just made up the numbers. Or it could be something is up with the die, i.e. it's loaded or weighted or something like that. Okay. So what kind of evidence do we have to support those conclusions? In particular, this bottom one, because we're going to assume poor Steve is not lying and it's not just random chance. We'll talk about why not in a minute, but we're going to assume that it's probably something's up with his die, like it's a loaded die. Now, what kind of evidence do we have? And this is the big key. So remember from section 6.2 that this is binomial, right? Where n is 12, you're rolling 12 times, and the probability of a 5 is 1/6, 1 over 6. So n times p, which is the mean number of 5s you expect, should be 12 times the 6, which is 2. And the standard deviation, the formula for that is the square root of n times p times 1 minus p, which turns out to be about 1.29. Okay, so we think Steve's has a loaded die for 2 reasons. One, he is far away from the mean. His z-score is 7.75, which we learned way back in chapter 3 is very unusually high. Very high. The other way you can think about it is his die is loaded because the chances of getting what he got just by random chance, by random accident, is really, really low. In Excel, it's this function. Binom dist, 12 successes out of 12 trials. The probability of success was 1/6 false. And you can see it's 4.59 e negative 10, which means it's 0.000000045,939, right? Lots of zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. And then a 4. Really small, right? Okay. So since it's so small, that gives us a clue that we think, no, something's up. Something's really up with this particular die. Something's got to be happening here. There we go. All right. So what does statisticians mean when they talk about hypothesis testing? Since it's something we're going to be working with for the rest of the course, let's think about this. So hypothesis testing is a procedure based on sample evidence and probability used to test statements regarding a characteristic of one or more populations. Chapter 10, it'll be one population. Chapter 12, or Chapter 11, 12, and 13, it's possibly one, possibly two, possibly more, depending on what we're working in. All right, so you make a statement regarding the nature of the population. You collect evidence to test that statement, and you analyze the results, which should sound very familiar because if you've ever been in a science class, that's sort of what you do, right? We make a statement about, how we think, this substance is going to work under, high heat or something like that. And then we go collect evidence, right? i.e. we perform a laboratory experiment or something like that and test it. And then we analyze the results of what we got, right? So if we think about our exploratory example, we assumed that all the dice were fair, right? And then we roll a dice, or in your case, you use Excel to do it, and we gather data on how many 5s we got. Then we analyzed that that data in a table and saw that Steve's data was very weird, right? It had a very low probability, and he was far away from the rest of the group. He had a very high z-score. It also would work with a very low z-score, basically just being far away from the mean. All right, so remember from chapters 1 and 3, and we've said this before in chapter 9, but I'll say it again. Parameter goes with population. So there are numbers that we want to know about populations. We want to know what percentage of people are going to vote for so-and-so. We want to know what the average lifespan of, an atom is. We want to know what the standard deviation of a certain stock is, that kind of thing. So we want to know those population values, but we can't get those population values. So we get sample values instead and use those to test the population values or make intervals for them from chapter 9. So in this chapter, what we do is we assume that we know the population parameters, and we assume that they're these certain values, whatever those are they're given. And then we're going to test whether they make sense in light of known sample statistics. So it's like, hey, I assume the average body temperature for people is 98.6. And you would assume that unless you can prove it otherwise. It's sort of like the game Clue, right? We're going to make assumptions about what's true in the world, and then we're going to go test them with evidence. Sounds like fun, right? Well, I hope so, because you're going to be doing a lot of it. Okay. So before we get into actually doing that long process for which you'd want that inferential statistics cheat sheet, we're going to get into some structure things. We have to be very precise about how we want to write our null and alternative hypotheses. So that's our first step. So remember that a parameter is a numerical summary of a population. So there are 3/4, it's really 3.5. Here, I'll put that. It's 3/4 parameters that of interest for us. Namely the mean, the population mean, what's the average, what's the center, what's the population proportion. That's a really big one, right, for polling, surveys, elections, all that stuff. Even, customer satisfaction surveys and things like that. That's proportion. The variance and the standard deviation. Now, this is where we get to the 4 thing, because variance and standard deviation are kind of the same thing. It's just that one is the square of the other. So, where standard deviation goes, there goes variance, because they go hand in hand. So they're not really different from each other. So that's why I said 3, because even though I know there's 4 things here, the bottom 2 are really kind of the same thing. All right, now, our null hypothesis is what we're going to assume to be true, right? So it's going to be a statement of no change, no effect. It's what you assumed to be true about the world. Like in our case, we assumed the dice were fair. So that's your null hypothesis, right? The alternative to that is H1. Oh, and by the way, the 0 is not, as in all for naught, right? So not N-O-T, but naught, N-A-U-G-H-T, or you can just say H0, right? Or the null hypothesis, right? Now, the alternative to that is that the dice are rigged, right? They're either one or the other. That's the alternative hypothesis. In general, remember this part, note, this is assumed to be true, the null hypothesis is, and in general, for our purposes, the alternative is what we're trying to prove. Okay? You don't have to bother proving a null hypothesis. A null hypothesis is already assumed to be true, so it's never really what we're trying to go after. We're usually trying to go, well, in our case, in our course, we're always trying to go after that alternative, because that alternative is what is suspect. Does this null hypothesis hold up or not? You assumed that was true. Is it actually going to work in light of real data? Now, there are 3 types of tests that we can run. We can run a right-tailed test, left-tailed test, or two-tailed test. So the right-tailed test is going to be, hey, you've got some parameter. Remember, parameters are the mean, mu, population proportion, p, or variance or standard deviation, sigma squared or sigma, is equal to some value. Always equals. Notice the null hypothesis always have equals in them. Always, because it's assumed to be true. The alternative is the parameters greater than, that's a right-tailed test. The parameters less than, that's a left-tailed test, or the parameters not equal. So in our case, with our dice example over here, you assume that the proportion of 5s, p, equals 1/6. So your alternative would be that it's greater than 1/6. That might be rigged, right? Or less than 1/6. That could also be rigged, right? Because you could be rigged to never roll a 5. Or just not equal to 1/6. You don't really care which way it was rigged. You just care that it is not what it should be. Okay, so this one would be weighted for 5s, right? That would prove that it's rigged. This one would be not weighted for 5s, weighted for 2s or something. And then this one would be, I don't care what it was weighted for, it isn't fair. All right? All right, so that's how we set up our hypotheses with symbols. So this is symbols, up here is words, and we'll do both, right, because they're both kind of useful, although we tend to stick in Chapter 10 a bit more to the symbol side of the house. All right, so let's read this problem over for a sec. Panels of jurors are theoretically drawn from a list of eligible citizens. However, in the southern states in the 1950s and 1960s, few African Americans were found on jury panels, so some defendants challenged the verdicts. During one such appeal hearing, evidence was given that 50% of jury-eligible citizens in the country were African American, but on an 80-person panel of potential jurors, only 5% were African American. The defense attorney argued before the jury judge that the panel was rigged. So let's write out these hypotheses. And I know I didn't say it, but let's do it in both words and symbols. So for us, it's that the jury was fair, right? We assume when you look at, say, on the news and they say, oh, so-and-so was convicted, you assume that that so-and-so had a fair trial, right? There we go. So we assume the null hypothesis is that the jury was fair. The alternative to that is that the jury was rigged. Now, how's it going to matter to us which direction it was rigged? What matters is, for this particular case, because these were African American defendants in the South in the 50s and 60s, it would be that the proportion for African Americans should have been 0.5, because that's what it was for the county. But it was rigged, possibly, too low. There were too few African Americans in that jury panel. And that's going to make it a left-tailed test, right? So too low, right? Rigged against these African American defendants by having too few African American people among the potential jurors. And that makes a left-tailed test. All right, let's stop right there, and we'll pick up with decisions next time.